Hi everyone, thank you for joining in our episode 3 of Courtside View. Today we will be talking about our data modeling basics. My name is Iman Bhattacharya, your host, Senior Global Product Marketing Manager from QIAGEN, and I have Ted with me. Hey Ted.
Hey, Mon, it's great to join you today.
Absolutely. Since we have some new people joining in today, why don't you go ahead and introduce yourself for a quick sec and then we'll get going.
Perfect. I'm Ted Johnson. I'm a data scientist here with the QDI organization here at QIAGEN, and I'm happy to talk about how we think about data modeling and some introductory questions you might ask yourself when you get started.
Absolutely. Well, data modeling basics for updates for biomedical knowledge base database structure involves defining and organizing data elements to enhance accessibility, integrity, integration across biomedical system. So with that, Ted, let's get going. What are we specifically talking about in data modeling basics?
Yeah, I thought today it might be interesting to start out thinking about how you understand your data and your use case. The questions you might ask yourself to get started. And then from there, we might think about choosing your implementation as a database technology. So do you need SQL? Do you need a graph? Do you need a document store? And then I thought we'd spend a little bit of time really thinking about the idea of one-to-one and many-to-many relationships and how that might inform, how you choose to model data and what you do with the data once you have your model.
For sure. So let's start with understanding your data part and start with some question. So let me ask you this. When you start on a data project, what are some of the initial questions you or one can ask themselves?
Yeah, so once you start with a data project, you first want to think about like, what are you trying to capture with this data? Yeah, you're making some measurements about people, about biology, about maybe proteins or genes. So what is it that you're trying to capture? What are you measuring? And then what are the interesting relationships between entities, or are the relationships interesting? Are you just trying to capture individual pieces of metadata, but for entities that kind of stand separately from each other? Or do you want to know, within context, how do these things that you're measuring, interact with each other? What do they do as groups? Maybe their interactions with other members of this data you're gathering is informative to answer your questions. Um, Similarly, you might want to ask, like, am I trying to measure properties of entities that don't change very much? You might think about, I'm measuring, geological locations and they're not going to move, versus I'm measuring kind of the dynamic state of RNA in cells under stimulus. Then you're going to have lots of change. Maybe your technology is going to advance as you're working on this, and so you're going to make different measurements in the near term future than maybe you're starting out with, right at the beginning. So you want to think about that kind of question once you start designing how you're going to store your data. Uh, because if your data is dynamic, that might mean that you need more flexibility in terms of schema design. Whereas if your data is relatively static and you know what you're going to do with it immediately right off the bat, maybe that informs your decision. Maybe you care more about being fast and accessing that static data, and you're not so worried about having to model new data, in the near future. Um, Similarly, is this data you're actively collecting? Are you going to need to learn more as you go, or have you collected all of the data and now you're really just trying to think about how you're going to analyze this existing data, and you don't need to worry again, if things are going to change, if you're going to take different measurements, um, something really is going to shake up your current data model, and you're going to have to react to it, in a short amount of time. These are all great questions to start thinking about. Once you start thinking about, here I'm going to embark on this journey to capture some data, to maybe start doing a new kind of analysis on it. How do I want to start working with that data? These are all where I would start.
That is really great. And then in the end, and in your slide is also showing that do you know ahead of time all data you will be interested in and what kind of metadata do you need to store? What do we or what would one learn by doing that?
Yeah, so if you know ahead of time all the data you want to capture, and you know ahead of time all the metadata you're interested in. And when I say metadata, we're talking about like maybe we're capturing whole files. You want to know, when was that image captured? How big is the image? What kind of color scale is the image on? Or, if it's a document, who produced the document? When was it last updated? What version are we on? Um, these are all crucial pieces of information that you might have if, for instance, you're updating a library of information, or white papers, or laboratory notebooks, for instance. Um, and so, knowing ahead of time, have I captured all that? Or is this product going to evolve? Is there going to be kind of new ways I want to measure this data? Is part of my goal to explore, what the data says about itself. That might inform then what kind of database infrastructure you need, to be able to attack that project.
Okay, thanks. So as a segue, I want to ask you that now that we thought about our data and questions, what we want to answer with it, and specifically how to choose a database.
Yeah. So as we jump into this idea of databases, I'm going to talk briefly about three flavors of database in pretty broad terms, without going into any specific technology you might choose inside that space. And really, the big three flavors you're going to think about are going to be SQL, or relational databases, and those focus on storing data in tables. And they might have this idea of joining between tables. So you have a shared identifier on table one and table two, and you might use that to link some of the specific properties you store in each of those tables. Um, and there's this idea of graph representations. So treating each entity as a node, that you connect with relationships. And you can think of, in detective movies where they have, their photos connected with red yarn, as they track a suspect. Yeah, that's an idea of a graph representation, which what you're interested in is those relationships between different entities. They could be people, they could be computer systems, they could be, linkages between proteins. Um, so graph is something you might choose if your real focus is on those relationships themselves and you want to know how each entity belongs in its wider context. And then there's this idea of a document store, and they fall broadly under this idea of NoSQL databases. And you might be storing literal documents, PDFs, images. You might be storing, JSON documents, so kind of the concept of objects. And these are convenient in that they are schema free, so you can change what kinds of metadata each document holds. And they have a relatively flat structure, which means you're looking up these documents individually, and you don't necessarily worry too much about how they're represented in relation to each other or in any sort of hierarchy. Um, really, each document is kind of its own entity unto itself. Um, and with that, you might start thinking about like, okay, how do each of these kind of broad ideas work into my thinking about how I want to proceed with my data?
Sure. So I guess as an obvious question is that these three kind of database, SQL, graph, and document store, what makes some of the strength and maybe weaknesses or limitations of these?
Yeah. So I hinted on these ideas kind of as I entered into this topic. And one of the things you want to think about as you thought about your data is, how do I want to access this data? What's my end goal? Am I hosting a server? And I want to be able to look up, individual facts quickly. Am I doing analysis? Do I want to explore through this data and learn how entities are connected to each other? So, in the first case, if you're doing SQL, then that usually is led by this decision that your data doesn't change a lot because SQL is locked in by a schema. You design that schema at the beginning. You say, what tables do you have? What data does each table hold? What data type does each column have? Is a column, numbers? Is a column words? And so when you lock yourself into a schema structure, then changing it becomes challenging, right? Sometimes if you need a new kind of table, or if you want to change how tables are designed, it's effectively a restart on that database, uh, which is fine if you know that your data is not going to change in the near term future, that you've really thought about that data structure and you know what the most interesting pieces are, and you're not going to be adding a bunch of new stuff, and no one's going to come in with more data that you hadn't thought of at the beginning, to add to this database, right? And then what SQL really excels at is looking up information, phone book style, where you're gonna choose an index and read over to a certain piece of information, and maybe you want to look up that same information for a bunch of entities, say phone numbers, real quickly. That's a great problem to solve with the SQL design. Um, Especially, SQL has an idea of joins, joining between tables. That's a way to understand relationships between different pieces of data. But if you're thinking about doing lots of joins, if your concept is really that you want to explore these relationships and learn from them, that can become very painful in SQL. You end up writing many join statements. Your queries can become really long. So what I would say is, if what you're really interested in is asking about relationships, then you should start looking at a graph database, right? And a thought experiment for this is like, am I asking questions about different sets? Like, let's say, I want to know of, people in my town where I've collected my data that live within 3 miles of Main Street. How many own dogs and drive Hondas? That's kind of three disparate pieces of information. In a SQL database, you would have stored that in probably three different tables, and you'd have to do some complex joins and filtering to get to that answer. And it's not impossible, but it's a little bit painful. When you write in graph, you're actually doing traversals through these things, and graphs are optimized to do traversals quickly. So capturing entities that share these three properties in one step instead of three. So that becomes a quick way to answer that. And that's true not just for data about people, but say data about proteins. I want to know about proteins that are expressed in the liver that, have association with inflammation and, are greater than 3 kilodaltons. That is a way you could ask a question easily in a graph that would probably entail lots of joins in SQL that you might find painful. Um, Similarly, if your data is going to change frequently, maybe you're in a discovery mode, and you might learn things about your data, in the near future that maybe isn't available to you right now at your database design phase. That's another place where graph infrastructure excels, because everything really exists as kind of a concept, what you'd think of as a node, and its relationship to other entities. It becomes really easy to add new kinds of information to the graph, whereas that would be a redefinition of a schema in a SQL setting. And similarly, if what you really want to do is answer questions by going through deep traversals, touching on lots of disparate pieces of data and seeing how they're related, that's something that graphs are good at. That's an easy thing to ask a graph to do. It's a challenging thing to ask a SQL database to do, especially if it's a novel question that maybe you didn't think about during the schema design phase for SQL. So if you're feeling like that's the kind of question you're trying to ask, that's another way you might point toward graphs. Similarly with document stores. Document stores are uniquely positioned to do fast lookups about pieces of metadata that are connected. So if you know that you're always interested in the same sets of information, and you're not really trying to traverse ideas that are necessarily connected, while you can do that kind of thing in a document stores really excel for fast lookups of sets of information where you just want to kind of collect that whole set quickly in your query every time. So that's a time you might look into more of a document store. And so, yeah, that's where I would start, and how I would kind of think about your questions when you choose a technology.
Thank you for explaining the details like of the strength and the limitations and specifically why should one go for it. But it sounds like what you explained, Ted, the kind of relationship in our data is super important. Can you expand on those a little bit?
Absolutely. Yeah, I'm a huge believer that the kinds of relationships you're working with should really define, how you analyze your data, how you choose to represent your data in a model. And I'd love to dive more into that idea. I'm going to start with this idea of a one-to-one relationship, and that is this idea that you have an entity, say it's Iman and Ted, two people, right?
Sure.
And maybe they have a number that represents them somehow. Maybe it's our employee ID, or maybe it's our cell phone number. Where in this kind of data world, we're thinking about like we're only ever going to have one of those things. If it's your social security number, odds are you have one. And when you design that system, you don't have to worry about things crossing over, right? Um, but you might also have this idea of a one-to-many relationship. So maybe if we're still thinking about Amon and Ted, maybe these are our phone numbers, and Iman and I have the same office phone number. You might call QIAGEN headquarters, but Iman also has his mobile phone that you might call him when he's traveling. So that would be an example where we have a one-to-many relationship, that you have these entities, these people, and they can own more than one of these properties, and they might even share one of these properties, like the office phone number. Um, and so that's an example of one to many, and both of those are things that SQL databases handle pretty well, right? So if you're in that world and you're saying like, oh yeah, all of my data, it really gets captured well in this idea of being one to one, that I don't see a lot of like crossover of these numbers, then you're pretty safe with a one to one or one to many, and you can represent those in SQL, and that data model's no problem. And even then, you can represent those in a graph structure as well, and you don't have to worry too much about it. That those are all easy to do. Where things get complicated is this idea of many to many relationships, and I decided for us to represent this still with people, so we have Amon and Ted in there, and this is a little social network, right? So we might say that Ted and Amon are friends, right? And we talk to each other as we do our podcast. Um, and maybe Amon has other friends. He talks to this coworker Alice, who's also friends with him. And maybe Amon and Ted both know Bob, right? And there's also this idea in many to many relationships where they might not share directions, right? So maybe we're I follow Bob, I think of him as my friend, but maybe that's not reciprocal. He doesn't pay attention to the work I do, and he's not tracking any of that, right? So that's a situation where if you find that you're trying to model this in SQL, it gets really complicated. You have to do kind of different tables to represent individuals. You have to find join tables that represent uh, these friendship interactions and whether or not they reciprocate. So you're now at least three tables, maybe four, depending on what about these relationships you need to represent, right? So that's a complication that might lead you to choose, say, a graph database instead of a SQL database. And it's also important to know, for your data model, when I think about these many-to-many relationships, are they inherently reciprocal? You might think of something in the social network setting like a marriage. Both people have to be married to each other. It's automatically reciprocal. Whereas maybe friendship or being a friend in like a Facebook setting, where you might follow somebody but they don't follow you back. If you need to model that kind of thing, then it's another argument in favor of maybe using a graph database infrastructure, where that idea is a little more native to the structure of the database than it would be if you were trying to model this in, say, a SQL or even a document store.
Fantastic. That's a great way of explaining one-to-one, many-to-many relationship. But that's just an example. When in the context of biological data, and when we talk about biological data, More specifically, what do you view as the ideal choice?
Yeah. So here I'm going to represent my own opinion, and reasonable people can disagree. Uh, but in my sense, I think that in biology, all of your relationships are many to many. And to illustrate that point, I'm going to pick on the central dogma of biology briefly. So we all get taught this idea that a gene leads to an RNA, leads to a protein, and it might be your first instinct to say, like, oh, there we go, Ted. That's one-to-one relationships, all the way down. One gene, one RNA, one protein. But then you start asking those deeper questions like, hey, when I think about this gene, do I need to represent the different alleles? Um, do I need to represent different variants? So like as a human, I will have two alleles for most genes. So just because I express one gene that we think of as having a given name or a given identifier, um, I actually have two copies of it. In most cases, one from each parent. Um, those might need to be modeled differently in our system. We might need to recognize that I have two different alleles of that same gene, and maybe you have two different alleles of the same gene that are even different than the ones I express. Like that's not an uncommon question to have to ask about biology. Similarly, variants. I might have two alleles, but I also encountered a mutation in one of mine. Uh, and it might be a somatic mutation that all of my cells are expressing, or it might be a variation that occurred during my lifetime. Maybe I got a bad sunburn and experienced a deletion in a gene. Um, so we might need to model that. So already we've kind of exploded from like, oh yeah, there was this one gene we had an idea for, we gave it a name, but now we see that we have to actually model it as many things. Similarly, there's this idea of translatable elements that are all over the genome, right? So I might have a copy of a gene that got moved from one location to another, during my lifetime. And I think a great example of this is actually you have cancer testes antigen A and B. They express a protein that, in terms of its canonical sequence, is identical, right? But they're different genes in different regions with different promoters. They're in different places on the genome, right? So here we have actually two genes that, depending on your data model, might run down to one protein sequence. So it becomes more complicated very quickly. And the same is true all the way down that central dogma, right? Once you express an RNA, you can have splice variation. You might cut out different sections of that RNA molecule and end up with a different protein, product at the end, depending on which splice variant, made it to the MR or the ribosome. Similarly, there's these ideas of capping and poly A tails and degradation of those molecules. Depending on how you're thinking about this data, it might matter to you, whether this RNA went capped or uncapped, and how long is its poly A tail. Similarly, you want to think potentially about, is this RNA modified after it was expressed? Then again, we have one gene makes an RNA, but you might have methyl and non-methyl versions of that same thing. That might be important depending on your user question, right? And again, all the way down to proteins. They exist as a functional unit, but when they get cleaved, their function might change. Think about like the complement cascade. C3A gets cleaved into C3A and B, and part of it binds cell membranes and helps kind of kick off the whole complement cascade and membrane attack complex. And the other part of it is chemoattractant. It attracts immune cells to the site of that bacteria or foreign body. So that's a functional thing where one gene produced what started out as one protein, but it actually became two functional units. And again, that gets us to this idea that all of biology is many to many interactions. And depending on the questions you're supposed to answer, you're going to want to change your data model to be able to adjust to those things. So that's one reason that I promote this idea that we should really think about modeling our biological data as many to many relationships, and that often means modeling in a graph database.
That's pretty cool. So why is thinking so much about data model is important? Why can't we just jump right into analysis and get to the work?
Yeah. I'm going to jump to a quote that I think a lot of data scientists are going to remember, and that's that all models are wrong, but some models are useful, right? And that really captures this idea that in data science, uh, we're trying to understand biology, and we can't, perfectly model it in our computer systems or in our mathematical models. But when we store data and when we capture data in a database, what we're trying to do is build a tool that helps us understand the biology. And the choices we make early on when we think about capturing that data and when we think about how we store that data is going to inform the kinds of questions we can ask easily, which might impact the kinds of questions we ask at all. Um, and it's going to affect how we answer that question and might impact then how effectively, we modeled the real biological system, how effectively do we get to an answer? So I think it's really important to take these early steps and think about data models and think about how to capture information before we dive in and actually just get right to the questions.
All right. I'll take your word for it. So let me ask you this. What's your favorite way to model biological data?
Yeah. Um, yeah, I think again that there are very few one-to-one relationships in biology. I'm going to say there's almost none, right? We're working all with many-to-many relationships, and we're trying to think about these ideas. Yeah, I'll jump into this idea that everything's a kinase is also a phosphatase. Proteins exist and we are interested in them because of the protein-protein interactions they have, whether they modify other proteins when they bind with them in complex. But even the protein-protein interactions we're aware of aren't necessarily the only protein-protein interactions any given protein has. The same gene regulatory networks. We might be primarily interested in kind of a canonical pathway, but that doesn't mean that it's the only way, a gene is regulated. Genes can have very complex upstream regulatory regions, right? A lot of them we're just now, coming to grips with. So when we choose a data model, I really emphasize this idea of we want to capture many-to-many relationships. And so my favorite way to represent this data is in some of those different graph representations we have, be it a properties graph or an RDF representation. And so that's something I encourage people who are thinking about building their own data models consider is, do you want to capture this complexity in biology? Is the data model you choose going to support you in understanding the real underlying biology that you're trying to capture?
Well, that's awesome. So now that we are quite the end of our episode, how do we, as in how can QIAGEN help our customers and our users in this journey?
Yeah. Not everybody loves to think about data models as much as I do. And we provide a number of data products where this thought process already happened, where kind of these key choices were made and tools were built. So, I point customers to ideas like IPA. If you need to upload your genetic data and do a pathway analysis, we have tools like IPA that support you. If you're interested in starting your own knowledge base, we have tools like the biomedical knowledge base to get you started, where we've made some of these key decisions to help get you kicked off on the right track. Um, Similarly, we can point to if you're looking for omics data. Our omics soft team did a great job collecting that cell single cell data and organizing it and structuring it and making it unified so that you can dive in and get to that important analysis you wanted to do. And as always, I'd love to point out our really strong services team. So if you want to get into our data products, but you're not sure how yet, we have a services team that will support you in getting started in your solutions. Similarly, if you have your own databases and you're like, wow, someone really needs to look in here and start kind of cleaning up and refactoring some of these things, we have a services team who's happy to engage with you and help you work with your own data to help get that in a way. that you can work with it more efficiently. So we're happy to help you really in any way you need help.
QIAGEN. Sample to insight.